So today we're going to talk about Newton's laws, but let's not give Newton credit because we already know his laws. We've figured them out ourselves, and you'll see that. The first law, I'm not going to read these verbatim off the slide because, again, we know these already, and we know them from like pop culture pretty much too. First one is just if there's no net force on an object, then its motion isn't going to change. And there's no delta V or delta P, however you want to think about it, but velocity. If it's at rest, it stays at rest. And if it's moving and there's no net force on it, then its motion won't change. That means it won't speed up, won't slow down, won't turn. It'll just continue on doing exactly what it's doing. First law, done. Second law is what if the net force is not zero? Then it says that it accelerates in accordance with this equation. We probably all know, like F equals ma is something that's said a lot. We'll see exactly what that is and see that it's what we've been working with this whole time. What this equation is a relationship between the net force and the change in motion of an object, which is what acceleration is, and that's what we've been doing with momentum charts, right? We know how to relate force and a change in momentum, so this is just kind of writing it in different language. And then the third law is, put simply, like every action has an equal and opposite reaction, and yeah, so that's also something we've seen implicitly a lot in like momentum charts, where if the net momentum change is zero, the total change in momentum is zero, then you have these two equal and opposite delta P's, which come from forces. And those forces are equal and opposite, we'll see. And so written like as simply as possible, if you have some force on object A by B, then there is always a corresponding force that is negative that force, which just means same magnitude, opposite direction. So just like flip the arrow to the other side of the vector. Now it's on object B by A. And this is always true for every single force. All right, so let's walk through them a little bit slower, one by one. First law, there's not really much more to say for it. If net force is zero, before we saw that delta P total is going to be zero, right? This is for like an individual, an object, or a system. And we'll define it on the next slide, but acceleration is a change in velocity. So delta P and acceleration are related. Turns out just by delta T and mass, but either way, delta P is a change in velocity, right, or a change in momentum, and so is acceleration. So that's really all the first law is saying. Second law, I said we've already seen before. We're just writing it a different way, changing the language, and that's true. This is something we've been working with for maybe months now, at least a month. F net delta T equals our delta P total, right? And this is just, you apply a force over time, and you get a change in momentum. We know what momentum is, right? We can break that up a little bit. Momentum is just mass times velocity. And now all I need to do is divide by delta T on both sides, so move the delta T over. And now I'm left with F net equals m times delta V over delta T, which turns out is the definition of acceleration. Acceleration is just the change in velocity over time, or the rate of change of velocity. This is what we'll get in, like the relationship between those two and between velocity and position. That's what you'll do more in DL, and then I'll begin next lecture with. That's like the equations and evaluating stuff. But today, again, we're just going to do like the meat and potatoes of it. So yeah, F equals ma is just F net delta T equals delta P, except in just like a different stage, just rearranging it a little bit. Yeah, so nothing new. Let's work with first and second law, and then we'll come back to the third law. So just to very concretely put the first and second law into perspective, or like into a physical situation, here we have a person pushing a box along the ground, and we're given that the box is accelerating to the right. So yeah, that's our starting point. Let's go ahead and label all the forces. Let's make a force diagram. So we're not doing angular stuff, so we can make our free body diagram where just every object is just a point. So we can just make the box, it's a point at its center of mass, and a force that we have is gravity, right? So force on the box by the Earth is always going to be straight down. But the box isn't falling through the ground, right? It's not like getting pulled toward the center of the Earth because it's sitting on the ground. And so we know we must have an equal and opposite normal force, which is F on the box by the floor. So these we would normally label like Fg and F normal. We're just being extremely explicit here because it's going to be important for this unit. But there's nothing different about these forces. They're not new. Note that while these two are equal and opposite, this is not what the third law is talking about. because these are both on the box. The third law would be saying that if there's an F on the box by the Earth, there is an equal and opposite F on Earth by box, which there is. It's just we don't care about it because we're concerned with the box. So the forces that we're labeling are the forces that are on the box. Okay, what else? Well, the person is pushing the box, so we have this force that's to the right, F on the box by person. And then finally, let's say there's some friction that's to the left, so F on the box by the floor in a different direction. However, we know that the force on the box by the person has to be longer because the box is accelerating to the right. So we'll see that in a sec, how that translates into the equations. But first, let's use the y direction to look at the first law, which is what happens when F net equals 0? Well, the motion doesn't change. And so this is also showing us that the laws all apply separately in x and y, just like any other problem we've done. These are vector equations, and so you can do in the y direction, Newton's first law, where F net y is 0, because gravity and normal force cancel out, or F on box by Earth and F on box by floor. And if F net y equals 0, that tells us that the acceleration in the y direction is 0, or there's no change in velocity in the y direction, or it's just always at rest in the y direction. Now we can use our second law to deal with the x direction, because now our net force is not equal to 0, but the second law is just telling us that F net equals ma. So in the x direction, F net is going to be the push force, F push. Maybe this should be F on box by person, but there's less space, so F push. And then in the opposite direction, so minus, we have the force of friction, right? Those are the two opposing forces, so this is our F net, and we know that's equal to ma. That's what the second law is, and we know that ax is positive because we're told that the box is moving to the right. So the box is speeding up to the right, and the exact magnitude of that acceleration is just related to how strong the push is, how strong the friction is, and what the mass of the object is. But because F push is bigger than F friction, this is positive, and so this is positive. All right, so pretty simple. This is something that we were already very well equipped to deal with, and now we're just kind of changing up the language, again, talking about it a little bit differently, but just drawing the parallels between these two models, if you will, of thinking about it. So let's do another one where now the third law comes into play a little bit more. So we have a cart with a fan, and we turn the fan on. It spins, blows the air, and the cart moves. Right? So first let's look not at what happens to the cart, but how the cart affects the air. Right? So I'm going to put this force here, and this is actually the force on the air by the cart. Right? The fan spins and pushes air molecules to the right, and so that's our starting point. That's what fans do. If I put my hand there, I'd feel the air moving toward it because of the force applied to it. Now here our third law comes in. If there is a force on the air by the cart, then there must be an equal and opposite force on the cart by the air. Right? So here's our F on air by cart in the positive x direction, and so F on cart by air is going to be in the negative x direction. And notice, I've drawn it down here, but this dot is now representing the cart. Right? So I would not put F on air by cart and F on cart by air on the same dot because they're two different objects. One's the air, one's the cart. And so, yeah, this is the result, and that if the cart blows air this way, the cart itself is going to feel a force and move the opposite way. And yeah, maybe we put in friction. So this is F on cart by the table. If the cart's rolling now to the left, maybe friction holds it this way. But as long as the force from the cart on the air is greater than the force on the cart by the table, then it will still move to the left. We can do the same thing with the y direction, just gravity and normal force cancel out, and apply the same laws before. So in the y direction, our first law, since the net force in the y is 0, of course the cart doesn't just magically go up or down. And in the x direction now, we still have our net force on one side. Our F net in the x is the force on the cart by the table, which is to the right, so positive. The force on the cart by the air, which is to the left, so negative, and that's equal to ma. And now we'll find that since the force on the cart by the air is bigger than the force on the cart by the table, this will be negative, the net force will be negative, and so the acceleration in the x direction will be negative. which doesn't mean it's slowing down. It just means that it's accelerating in the negative x direction. And so, of course, this cart will pick up speed moving left. All right, so this example combined first, second, and third law. Again, it's a situation that we were already equipped to deal with. It's just reframing it in these terms. Final addendum to this. Why? Let's say I wanted to make this go faster. Can I just put a sail on the right end of the cart? So I just place a vertical sail on the right end of the cart to catch the air that I'm blowing. So now I'm getting twice the power, right? I blow the air, that speeds me up. The air hits the sail, that also speeds me up. Will that work? If I put a sail there, will this cart move twice as fast or even any faster at all? Yeah. Yeah, you're exactly right. If we put a sail there, the force on the sail by the air is going to be exactly equal and opposite the force. I guess that's F on sail, but the sail is attached to the cart, so it's also on the cart. These two are going to cancel each other out. We'll get nothing. So from the force perspective, we can say, here's the F on the cart by the air. We know that there's an equal and opposite F on air by cart. Right now the air is moving across through the cart. And then when it gets to the sail, it produces this F on sail by air that is in this direction now. And then there's also an equal and opposite F on air by sail to the left that brings the air to a stop. So with this situation, you have this net zero where you're just giving the air some, so now I guess switching to the momentum way of thinking of things, the fan dumps some momentum into the air. And since there's no net external force, that means that the cart gets an equal and opposite amount of momentum. Right? So now the cart and the air have exchanged some momentum, but putting the sail there just makes the air dump the momentum right back into the cart. And so we end up not exchanging any net momentum. And so if they started at rest, they're going to stay at rest. So you can't just create free energy out of nowhere. And the F net here is 0 because, again, there's no external thing. Like before, the air was this external thing that absorbed some momentum and gave momentum to the cart, but now it's all self-contained. Makes it a closed system, if you will. Okay, so just another example of something that we've seen many times, but now expressed in terms of Newton's laws, or maybe just seeing where Newton's laws come up here. A cart 1 collides with cart 2, which was initially at rest, and then they stick together and keep going after. Right? We've seen this a million times. The momentum chart shows us that all the momentum is initially with cart 1, because cart 2 is at rest. And so here's our total momentum, just whatever cart 1 has. There's no net external force. It's just two carts colliding. So the total final momentum is the same as the initial. And since they stick together, we know, and if they're the same mass, just half of the momentum is going to go with one cart, half of it goes with the other. And so going back to the delta P column, that tells us that cart 1 gives up half of its momentum to cart 2, and so it reduces its momentum by half, and cart 2, gaining that half of momentum, speeds up to whatever the cart 1 slows down to. They meet in the middle. And so if we look at those two equal and opposite delta P arrows, those translate directly to equal and opposite force arrows, right? Because what is delta P but an F net times a delta T, right? So we have this third law coming in that F on cart 1 by 2 is equal and opposite F on cart 2 by cart 1. The only, the last missing piece that I haven't addressed yet is the delta T, right? The relationship between these equal and opposite forces and the equal and opposite momentum exchanges, delta P's, is this delta T. So if the F's are equal and opposite and the delta P's are equal and opposite, that tells us that the delta T's must be equal. We don't have two different times. And the way to explain that is, two things are colliding. By definition, the collision, it lasts the same amount of time for both, right? If object 1 is in the process of colliding with object 2 still, then object 2 is still colliding with 1. And as soon as 2 is no longer in contact with 1, 1 is no longer in contact with 2. Or if they stay in contact, so what I mean is like the collision is just one thing. There's only one time interval that it occurs over. And so the delta t is the same. And so, yeah, if the delta p's are equal, the forces are equal and opposite, I guess. So yeah, tale as old as time, but new framework. Now let's try kind of a tricky clicker question. So we have an adult and a child playing tug of war. Which of these is a correct explanation? And I strongly encourage you to think about it first, come up with a guess, talk to your neighbor, but you should try to explain whatever answer you have or test them out by making force diagrams for each of them. So you can just make a dot for the adult, a dot for the child. What should the force diagram look like for each one of these situations? And does that correspond to what the situation says will happen? Setting up for one. I'll give you 15, 20 more seconds. All right, you did really nicely with this one. And that doesn't, if you get it wrong, I don't mean to say only the people that got it right did nicely. I just, as a class, we're going in the right direction. But kind of the purpose of, I think you learn more if you get it wrong. Not that you lose out, because then you already have the information. But what I mean to say is, I don't think it's relevant to how well you're doing, whether or not you're getting clicker questions right. Of course, I say that on the last day of the quarter, this insight that I have. Anyway, it's not the last day of the quarter either. Don't stop going to class. That just wasn't true. Anyway, first let's address something in here, is that a lot of these mention a friction force on someone. It's not clear to me where friction comes in tug of war. Does anyone want to help me out with that? What friction did you interpret that to be? Or even not the direction, what is the friction between? Exactly, that's it. It's the digging the heels or the toes, depending on their technique, how it's the connection with the ground. So if we imagine tug of war just in space, two astronauts floating there connected by some tether, if they tried to play tug of war, they both pull, right? And they both experience a force toward the center, yeah, and they'll just come together. They might not come together with equal accelerations, right? Because we know F equals ma. So if the forces are equal, they both tug the rope, they both get pulled by the same force, the heavier one is going to move slower, which that makes sense in our momentum framework as well, right? If you apply the same force over the same amount of time, you give the same impulse to two things, or at least equal and opposite, the heavier one is not going to move as quickly. But either way, there's no way to win tug of war in space, because no matter what, any force applied to you is going to be a net force, and you're going to move. However, when you are on the ground, you can dig your feet in, you get friction with the ground, and so as you're tugging the rope and the rope's tugging you back, as long as you can counter that force from the rope with the friction, then you won't move. Or maybe you walk the opposite way. The friction wins, and you win tug of war. And so the answer ends up being C, that the child will win if the friction force on the child is bigger than the tension force. And so our force diagram here, it would be easier if they were all just drawn on one point, but in the y direction, again, uninteresting, gravity and normal force cancel out. But in the direction of the tug of war, the tension is going one way. That's the force from the rope on the child. Face the same way as the child. That's the force from the rope on the child. And the friction is the force of their feet against the ground, keeping them from moving in the direction that the tension wants them to. And if the friction on the ground by the child is greater, that means the net force from the on the child is to the left or to the right, in the direction of the friction. And that means they'll accelerate that way. In other words, the child will walk backwards and win tug of war, pull the adult, pull the rope toward them. And so we could talk about third law here. So if there's an F tension on child, that could we can say that is like the force on the rope, force by the rope on the child. That means there's an equal and opposite force on the rope by the child. And then that's going to translate to a force on the adult by the rope. And there's an equal and opposite force on the rope by the adult. What I mean to say is if two people or anything are connected by a rope or a chain or whatever with tension in it, they're both going to feel the same force, equal and opposite, right? So however hard the child pulls on the rope is pulled by the rope is exactly how hard the adult is pulled by the rope or pulls on it, right? So as long as they're both holding on the rope and it's not slipping through their hands, they're both feeling the same force from the rope, which might be counterintuitive. The only difference between the winner and loser is how that force from the rope, the force from the tension or by the rope on the child, compares to the frictional force that keeps them planted or makes them move in the opposite direction. So maybe we could also talk why would we normally think that an adult would win tug of war. If no matter how hard the adult pulls, which is probably they have more strength than the child, no matter how hard they pull, the child is going to exert the same amount of force equal, that's just how the third law works. Why would we normally think an adult is going to win tug of war? Well, you win, we just decided, by having more friction, by being able to overcome the tension force with friction. And we've only done this a little bit, but what is friction normally related to? It's the normal force. Something's mass, it's weight, right? The heavier something is, the more it's pushing down. Friction is normally, you're not responsible for this, but friction is normally some coefficient of friction times the normal force, so the force of contact. And so the heavier someone is, the easier it'll be for them to create friction with the ground. So maybe the child is wearing cleats and the adult's wearing flip-flops with butter on the bottom or something, but it doesn't matter. As long as this is the case, the force of friction is bigger, child wins. Okay. The other D describes a case where it's just the opposite, where the situation described is the adult winning. If the frictional force on the adult is bigger than the tension on the adult, that's not true. And E, the child wins when the tension is bigger than the tension on the adult, which we decided that's not even possible because the tension force on each of them is equal. It's just the frictional force that's different. And then finally, the reason that does not violate the third law is because F on friction by the ground on the child, so F friction by the ground on child, that does have a third law pair, which would be F on the ground by the child, but it's just that. It's on the ground. So that is not equal and opposite anything having to do with the adult, right? So that frictional force doesn't automatically cancel with the adult. And the adult has their own F on the adult by the ground friction force that has its own F on the ground. But those are all just absorbed into the ground, and those affect the earth, which in minuscule ways. They have nothing to do with each other. Okay, questions here. We got a lot out of this little example. Okay, So now we're going to do a little thought experiment, and first we'll do our control. So we're just exploring what happens standing on a scale, what it's going to read in an elevator moving up and down. But to do that, we first need to think about what's going to happen when the elevator is at rest. So just how does the scale work normally? So we have a person standing on the scale. We know it's on Earth, so the person is always going to have the force of gravity pointing down, so F on person by Earth. But they're at rest, so we know the net force is 0. And the reason is they have also a normal force that's pointing up, the F on the person by the scale. So that's the force diagram of this person as they're standing on the scale with no net acceleration. And so if they're not accelerating, they're at rest, then we know that the person has no net force on them. So we know that F on person by the scale and F on person by the Earth must be equal and opposite, like we just said. And so that tells us that the force on the person by the scale, this upward force here, has magnitude mg, right? Just equal and opposite gravity. And so now we can use our third law. If there's a force on the person by the scale that's equal to mg, there's a corresponding equal and opposite force that's on the scale by the person. And that is going to be equal to negative mg, right? So gravity pulls down on the person at mg, the scale pushes up on the person with mg, and as a result, the person pushes down on the scale with mg. That might seem obvious, like we've just done a bunch of torque problems, right, where you just if there's a mass on a beam, you know that it's just going to exert a force equal to its own mass times gravity. So we don't do these 3 steps, but you could if you want, of first and third law. Anyway, what we figured out is the force on the scale by the person is mg, and what we want the scale to read is just m, right? So what the scale is doing, we figured out the purpose of our control here is how a scale works, is that it takes the force that it feels from whatever's standing on it and divides by g, right? So let's say I weigh 50 kilograms, I step on the scale, gravity pulls me down with a force of 50 times 10, so 500 newtons. And since I'm not moving, I know that the scale must be pushing up with 500 newtons, right? So my net force is 0. And since I'm being pushed up by the scale with 500 newtons, that means I'm pushing down on the scale with 500 newtons. And because I want the scale to read my mass of 50 kilograms, all it needs to do is divide that 500 newtons by 10 meters per second squared, and you will indeed get 50 kilograms. So a scale interprets the force on it, divides by g. That's our finding. So now, let's see what happens when we are in an elevator that's moving downward. Not just moving downward, but accelerating downward. The title kind of gives away what's going to happen, but let's go ahead and prove it. So now the person's on this elevator. They still have 2 forces on them, gravity pointing down, normal force pointing up from the scale. Except now, instead of our first law, we use the second, because there is a net acceleration. The person is in an elevator that's accelerating down. So I think it's kind of trivial that the fact that there is a separate first and second law, because the first law is just what happens when acceleration is 0, and I don't think you need a separate law just for putting 0 somewhere. Anyway, that's just my personal opinion. But anyway, our net force on the left equals ma, so net force is force on the person by the scale, that's pointing up, and force of gravity, so minus F on person by the Earth, and that's equal to a negative number, right? Because we're given that the elevator, and thus the person, are moving downward, or accelerating downward. So we know that the F on person by Earth is always mg, right? That has nothing to do with the motion, that's just the force of gravity. And so I can move that over to the other side, and I find that the net force, or not the net force, the force on the person by the scale is now not mg, but mg minus ma. It's slightly smaller than it was before, and it's slightly smaller in magnitude than the force of gravity, which makes sense, right? Because we want the person to have an acceleration downward, and so whatever the force pulling them downward must be a little bit stronger than the one pulling them upward. Otherwise, they wouldn't move at all. And so that's why the force from the scale is not equal and opposite, it's just opposite and a little bit less in magnitude. Now we'll do that same little trick. If the force on the person by the scale is mg minus ma, the force on the scale by the person is just equal and opposite that. The third law still works. And so that the force on the scale by the person is going to be less than mg. It's going to be mg minus ma, pointing down. Right? So now if the scale isn't pushing the person as hard, the person's not pushing on the scale as hard, the scale is going to feel a smaller force as the elevator accelerates downward. And so if you divide by g, the scale is going to read a number smaller than m. And you can try this. If you go in an elevator and you're starting at rest and you press a floor lower than the one you're on, as the elevator starts to accelerate downward, the mass that the scale reads will drop while the elevator is accelerating downward. Now let's flip the situation. What if our acceleration was upward? Same steps. Second law tells us our net force in the y direction, F on person by scale, which is up, minus F on person by earth, which is down, equals ma. Now a is positive, right, because we are accelerating upward. And so we can do the same thing. F on person by the earth is always mg. That's just gravity. And so we move it to the other side, and we find that now the force on the person by the scale is bigger than mg. It's mg plus ma. The reason being, again, we want the person to accelerate upward, so we need their net force to be positive. And so the force on the person by the scale not only needs to cancel out gravity, but needs to go further than that and have some net force upward. Now, third law tells us that if the force on the person by the scale is bigger than mg, the force on the scale by the person is also bigger than mg, and so it's going to read a mass that is bigger than our true value. And same thing, if you go on the elevator, stand on a scale, and press a floor above you, as the elevator starts to accelerate upward, the mass that it reads will indeed go up. Couple things to note here. One, I mentioned this before, but it's important that the elevator is accelerating. It is not just that it's moving. So maybe we can tap into our experience here. If you go on an elevator, when it first starts moving upward, you feel a bit heavier. When it first starts moving downward, you feel a bit lighter, right? You feel that like emptiness in your stomach sometimes. But that doesn't last for the whole ride. We can all go over to the physics building after this and try it. When you get on the elevator, you first press the button when it first goes from 0 to like positive velocity, or 0 to negative velocity, going down, something like that. That's when you feel like the heavier or lighter. Once it reaches its traveling speed, things get back to normal. Until it's done, and let's say you're going up. If you're moving upward at a constant velocity, your net force can still be 0, right? Constant velocity means no change in velocity, no net force. Once you reach your destination, you need to come to a stop. So you'll be going from a positive velocity to 0, or you'll have a negative acceleration. So in that case, if you're moving upward, when you first start going upward, like we said, you feel heavier, but then when you come to a stop, you feel lighter again, just for a sec. So it goes like normal, start moving, feel heavier upward, and then for a split second, feel lighter again, and then stopped. And the inverse would go for going downward. The elevator first goes from 0 to a negative velocity. That's a short period of negative acceleration where you feel weightless. Then it's just constant traveling speed, you feel normal. And then when you reach the bottom, you're going from a negative velocity back to 0, where you're stopped, which is a positive acceleration, which makes you feel heavier for a sec. So this is the type of graphic, like you'll graph stuff like that and see the implications of that in DL, and then that's where I'll pick up next time. But thinking about the relationship between acceleration and velocity is going to be a very important skill for you, especially qualitatively like that. What other thing? Okay, yeah. So just moving on from here is final piece. Can we be weightless in this case? We said we can increase and decrease our weight, or like perceived weight, what the scale reads, by moving an elevator, accelerating an elevator up and down. Can we be weightless? Well, if we set up our same equation, the way you do it, this is kind of working backwards from the answer, but if we say that our acceleration is negative g, so that our net force equals ma, and that a is negative g, you end up finding that the force on the person by the scale equals 0. Maybe it would have made more sense to work backwards, demanding that our acceleration demanding that the force on the person by the scale is 0. What does that tell me my acceleration has to be? Anyway, the takeaway is that the scale will read 0 if you are accelerating downward as fast as gravity wants you to. In other words, if the normal force is 0. So if the scale isn't pushing you back up at all, meaning the net force on you is just the force of gravity, which is free fall, then you're not pushing back on the scale at all either, because the equal and opposite 0 is just 0. And so if you just snip the cord in the elevator and you fall, then you'll feel weightless and you'll fall at an acceleration equal to g. And so that's why free fall feels weightless. And it turns out, I think it's kind of interesting that our perception of weight, right, when we feel heavier or lighter, it really has to do with opposing forces, right? We feel heavy, or we feel like we have mass when we have 0 net force, right? We're all sitting here, we're not accelerating up or down, and gravity and normal force are fighting against each other, and no one's winning. Net force is 0, but we feel this compression, right? As gravity pulls us down, but our cells are all just pushed up against each other, right? That's our interpretation of weight. If we drop the floor out from under us and fall, it's weird, the net force then is now not 0, but that's when we don't feel any force, because just one force is winning and we accelerate. There's no none of this compression that's happening, if that makes sense. So yeah, anyway, that's our interpretation of weight, is the counteracting between gravity and normal force. So one last thing, this is kind of outside the bounds of this class. It's just interesting to note that you have 2 examples here, a person in an elevator. We can imagine it's us in this classroom right now. It doesn't matter. But we're in a closed box, and we can't see outside. So we can't see there's nothing to look in reference to. In one case, we're just stationary on Earth. I guess we don't have proof, but that we all assume we are right now. We don't know what's happened since we came into this building. But we're stationary on Earth. Gravity's pulling us down. We feel like we normally do. We feel some amount of mass. And if we let go of a ball, it will fall with acceleration negative g. Now take the not opposite, but another example where we're in this box, but we're in space. And there's no gravity, but we are accelerating upward with acceleration equal to g, 10 meters per second in the upward direction. These 2 would feel exactly the same. So we could go through that same mass, or the same equations we did on the previous slide, and we'd find that if our acceleration is g, and there's no gravity, you'll get the same force on the person by the scale, the same normal force, which is what we said is that's our perception of our weight, is what normal force we experience. And if you are in this situation and you let go of a ball, it will indeed fall to the floor. It might be more natural to think about that as you let go of the ball, and now since it's not connected, nothing is accelerating it up, but the box around it is still accelerating, so the box comes up and meets the ball. But there's actually no experiment that we or this person could do to distinguish between these. The physics inside these boxes are 100% identical, and there's nothing you could do to figure out which one of these is true without seeing an outside reference frame. So I think that's interesting. Another extension of that is that this is another version of the equivalence principle, is that we've only been talking about one mass, and it just kind of makes sense that your mass is your mass. But we use it in multiple places. One is the gravitational mass. That's just me saying you have a massive object on Earth, and it's going to feel a force equal to m times g. So mass there is it's some characteristic of the gravitational force that just determines how strongly objects pull each other together based on this value, mass. Then there's your inertial mass. That's the one in F equals ma. That's the one that says, if I apply a force to this object, how fast will it accelerate? And based on F equals ma. So it's if I apply a force to an object with a large mass, it will accelerate slowly. If I apply the same force to an object with a small mass, it accelerates fast. That concept of mass, which tells us it's inertia, how hard it is to move it. And we've just talked about them the same way. They're both measured in kilograms, so we just kind of assumed, yeah, why wouldn't it be the same m? But if you think about it, like, there's no reason why those have to be the same thing. One's just a measure of a fundamental interaction, right? Like charge, and that determines like electricity, and like that determines the repulsion and attraction. That's like gravitational mass. That's just like how this force happens to work. And then the other one is how it responds to forces. So I don't know. They turn out to be the same thing. So it is a good assumption that we made, and that's been measured to like a really, really high level of precision. But yeah, if you noodle on it for a bit, I don't think there's a reason that you can just like assume that they're the same thing. Anyway, that's not part of this class. I just think it's interesting. Okay, questions on the stuff we've done on these slides. Like I said, this is a good foundation. You're going to go into much more mathematical applications of this soon. I guess this slide's kind of that. So I won't read this one out loud, but you have some details about a car hitting another car. I'll give you a sec to think about this and talk to your partner or neighbors. Two bits of guidance for this one. One, because that's what we've been doing this whole time, I recommend trying a force diagram or trying to set something up that has a visualization of it. And the other is, once you think about it from this like force perspective that we've been talking about, force and acceleration, go ahead and try to like think about this problem in our momentum framework. Like if this was just a normal collision between two carts and you were setting up a momentum chart, try to approach it with that thinking too. Because as we've learned, those two things are analogous. They contain the same information. I'll give you one more minute with this one. And perhaps I am hinting with the one more minute that this is a tricky one. Okay, I'll stop us there. So we did succeed. Originally, answer B, and again, nothing to feel bad about if that's what you answered or any of them, but answer B is wrong, and it started off as by far and away the most popular answer, but we did alter until E became the most popular answer, and E is the right answer. So let's discuss why. I think A and B like right away make a lot of sense, and that shows that you're like paying attention and thought about it, which is good. We've learned so far that F equals ma, right? And so I see in this problem a mass and an acceleration, and I'm asked about a force. So it makes sense to multiply them together. I get 8,000, and then the car is moving to the east originally before the collision, and so the force that acts on that car by the other one is probably just right back the way it came, right? So 8,000 newtons to the west, done. Not actually the case. I would think, so let's what are these two numbers? Like, what is the information that we're given actually telling us about? So 2,000 kilograms is, of course, the mass, but the 4 meters per second is the acceleration before the collision. So we can ignore the existence of the other car altogether. Say I'm the first car, I'm moving to the east at this 4 meters per second squared. That means I'm accelerating to the east. That means I'm speeding up. And where is that force coming from? That's F on me. So there is indeed a force. The net force on me is 8,000 newtons. And it is actually to the east because I'm accelerating to the east. What is the force on me that's causing me to accelerate 8,000 newtons to the east before the collision? Why does a car accelerate? Like, where does that force come from? Yeah, exactly. I mean, like, the energy comes from the engine, but like, no matter how powerful the engine was, if you just put a car floating in space or like on ice or something, it's not moving. You need the wheels to have some friction with the ground, and it's kind of counterintuitive, like the rotation and stuff, if you were to map it out. But the car moves because it pushes against the ground and moves one way, and it provides an equal and opposite force against the ground that we normally ignore because it's the Earth. But that's what that force means. So that 8,000 newtons to the east is a legitimate, and the one to the west. Those are both real forces in this problem, except they both happen before the collision, which is not what we're concerned about. We want to know what the force is on one car during the collision. So that's not right. But the one to the east is the force on the car by the ground before the collision, and the one to the west is the force on the ground by the car. Does that make sense? So A and B do exist in this problem somewhere, but they're not exactly what we were asked about. Okay. So the answer is E, and the reason is we don't know what happens in the collision, right? So like we know there's elastic, inelastic collisions, everything in between. We've seen examples of one thing hitting another where they stick together and keep going, like we just saw. The first thing can bounce off and go the other way. They could even gain some north-south component as long as they cancel out, right? Because the momentum here total is just to the east, whatever the speed the car was at before it hit the other one. An infinite amount of possibilities could happen and still conserve momentum. We need more information. And that's what I was getting at, where if you try to solve this problem using like a momentum chart and that way of thinking, which again is equally as valid, you simply do not have enough information. You don't even know how fast the first car is moving. You just know that it's getting faster at a rate of 4 meters per second squared. So you don't even know how much momentum is in the system to begin with. Yeah?
So we need to know the initial and final velocities before having the collision in order to figure out how much force was exerted on that car to change it.
Yeah, exactly. The initial and final velocities were like numbers that gave you those, like something like that. Yeah, exactly. So, whoops, what am I doing here? F doesn't indeed equal ma, but for the during the collision forces that we're looking for, we just don't know what the we don't know how the car's motion changes during the collision, which is what we want to know. Even if we were told the car comes to a complete stop, that still wouldn't be enough because, like I said, we know the acceleration, not the velocity. And so this is something, again, you'll work in DL and then we'll talk about it next time more, but acceleration is the rate of change of velocity. It's like the slope. It doesn't actually tell us what the value of the velocity is. We don't actually know what the car's momentum is. And likewise, we don't know how long this force is applied for. So even if we did know the car's original velocity before it hit the car, and we're told that it came to a stop, we couldn't tell the force on that car unless we knew the delta t. So there's really a lot missing from this problem that tells us that. And then this math doesn't teach us physics with that. What I'm really trying to get across with that, or what Dina, I guess I didn't mention this in this lecture. I borrowed these slides from Dina, who is another 7 Series instructor. But math doesn't teach us physics, meaning that our momentum as I just demonstrated, our momentum framework that we talked about earlier does not allow us to solve this problem with this information, and this new acceleration framework doesn't either. The reason being they're the same thing. They're just mathematical different ways of expressing it. It's the same amount of information, and so we can't just learn more by rewriting it, is what I'm trying to say. Okay, so yeah, just going more into detail with this. Beforehand, the first car is moving forward because there's a force on that car by the road. That's where the 8,000 newtons comes into play on the car to the east and on the ground to the west. Right before the collision, the Cart 1 has accelerated up to some final velocity, which we don't know what that is, but we would need to know if we wanted to solve this problem. During the collision, there is equal and opposite forces at play. There's a force on 2 by 1 that's going to be probably to the right, F on 1 by 2, which is going to be probably to the left, but we don't know. Again, these could have some north-south components, something like that, as long as they cancel out. Anything is physically allowed. Yeah, so objects don't carry forces. Yeah, you should be wary of that. That when you're trying to connect motion to forces, you need change in motion. Just like one value is not going to do it. Okay, now this is the last one. So 4 different scenarios here. Pick which are yes and which are no. And try to come up with an example. All right, so with the time left, my little hint here is that the answer is A. They're all yes, but I want to divide and conquer. So if you're sitting over here, you and your neighbors try to come up with an example that shows that 1 is possible. For the people in the middle, but on like this side here, try to come up with an example for why 2 is possible. 3 and 4. I'll give you about 1 minute for this. $30 seconds. All right, I would love, ideally, to have people explain them themselves to the class, but in the interest of time, I'll just put a few up here. I hope your conversations were productive. But for 1, can the velocity be 0 when acceleration is non-zero? Yes. One example, I'm moving right now in the positive x direction. I'm going to slow down, stop, turn around, and start moving in the negative x direction. That whole time, my acceleration was negative. I went from having a positive velocity to a smaller positive velocity to 0 to negative. So my delta v over delta t was negative. And so my acceleration was negative the whole time, non-zero, but my velocity was instantly at one point negative. So that's possible. Can the velocity be to the right and acceleration to the left? Sure. I'm moving to the right, but slowing down. That was just my acceleration to the left. In other words, decreasing my rightward acceleration, even though I'm moving to the right. Can speed be constant and acceleration be non-zero? Circular motion. We saw when like a tennis ball was swinging in a circle, its linear velocity is constant, right? It's moving around the circle, tracing out a path with a constant linear velocity. But at every point in time, that velocity is constantly changing direction. And that takes acceleration. That is a change in velocity. And so it has a constant speed, but a non-zero acceleration. And then finally, can acceleration be perpendicular to velocity? Same exact thing there. In the case of a ball moving in a circle, the ball's instantaneous acceleration is always tangential to the circle, and the acceleration vector, the instantaneous velocity is always tangential, and the acceleration, or the force, was always directly pointed toward the center. And so that force tugs the velocity in a circle. And so this is where we'll pick up next time. In DL, you're going to do a bunch of equations and stuff. It looks new, but it's really, this stuff is more math than physics. The stuff we covered today is the real meat of the physics. And then, after we finish this next time, the rest of lecture will be just a rapid-fire review of important slides from throughout the quarter.